Kumar, and today, together with my teammates Upmanyu and Sanjay, we'll be presenting our project for CMOS analog IC design. Our project is titled 0.5 volt 17 nanowatt bulk driven operational transconductance amplifier for biosignal processing in 180 nanometer CMOS technology. I know that's a mouthful, so let me break it down for you and tell you exactly why every word in that title matters. Let's start from the very beginning. An operational transconductance amplifier, or OTA, is one of the most fundamental building blocks in analog circuit design. Unlike a voltage amplifier, an OTA converts a differential input voltage into an output current. That output current is given by I out equals GM into V differential, where GM is the transconductance. OTAs are the backbone of continuous time analog signal processing. You'll find them in active filters, oscillators, data converters, and most importantly for us today, biomedical front-end amplifiers. Now, here's where it gets interesting and where the actual engineering challenges lie. Wearable and implantable medical devices, think ECG patches, EEG headsets, pacemakers, run off tiny batteries. These batteries need to last months, sometimes years. That means the analog front end has to operate at extremely low voltage supplies and consume power in nanowatt range. But here, the fundamental problem lies with conventional OTA design. In a standard CMOS process, including our 180 nanometer technology, the threshold voltage VTH of a PMOS transistor is approximately zero point 0.5 volts. A conventional gate-driven OTA needs the input common mode voltage to sit at least 1 VTH away from the supply rails. Do the math. If your total supply is zero point 0.5 volts and you need zero point 0.5 volt of headroom for VTH, you have literally zero room for any input signal. Conventional design is physically impossible at this supply voltage. So the question becomes, how do you make an OTA work when the threshold voltage is the same as entire supply? That answer what that answer is what this entire project is about. And Sanjay will go deep into the circuit level solution. But first, let me hand over to Upmanyu, who will tell you exactly why solving this problem matters in the real world. So Sanjay, yeah, it's
Thank you, Akhil. So let's talk about why this matters. So the real world context that drives the engineering constraints you have just heard about. So the global wearable device market is like very enormous and growing rapidly. We are talking about ECG monitors, ECG brain-computer interfaces, prosthetics, pacemakers, all of these, all of this, and they share one common thing. That is, they need to sense very weak biological signals in real time, continuously, and that too with very minimum power. Now let's trying to amplify. Now, biosignals are fundamentally different from signals in digital systems or RF communication. An ECG signal, the electrical activity of heart sits in the frequency band of about 0.05 hertz to 150 hertz, and its amplitude is in the range of 0.5 to 5 millivolts at the skin surface, and that's like very tiny, and that's uh, like 3 times smaller than the usual uh, signal. So what happens is that ECG signal at the brain activity is even weaker, like from 10 to 10 microvolts. Now these signals also coexist with common mode interference. So our body acts like antenna, picking about 50 to 60 hertz frequency as common mode noise, often 100 of millivolts, 1000 and then this is why we need to have a common mode rejection ratio, which is the most critical specification for a biomedical OTA. Now we need the amplifier to amplify the differential bias signal while completely ignoring that common mode noise. Now the power consumption drives everything in this domain. An implantable device like pacemaker cannot be recharged easily. It runs off a battery that usually has to last for 7 to 10 years. Now, replacing a pacemaker battery requires surgery. So when the front end OTA draws 70 nanowatts instead of let's say 1 microwatts, that's just not a number. That's an years and years of extra battery life that we're adding, and we're avoiding an extra procedure in order to add the pacemaker. And wearable device also benefit enormously as a patch that lasts 2 weeks instead of 2 days becomes very viable. So the engineers have tried several approaches to solve the low voltage input edge problem. Let me quickly walk through them. First, we have used this floating rate transistors. Now, these allow effective threshold voltage to be programmed electrically. Clever, but they require like UV light to erase, which is practical in most production flows. Then we have used quasi-floating gate, which is similar concept, but it is without UV eraser requirement, and it brings its own biasing. Then that dynamic threshold MOSFET. Now, what happens? They said it ties the gate to the body to dynamically lower the threshold voltage. It works, but it limits the supply voltage to around 0.6 voltage due to forward junction current, and it doesn't scale very well. Now, the approach we have used in the project is the bulk-driven technique. It is the most practical solution at it as it requires no process modification whatsoever. It works at any standard CMOS process. It's been validated by researchers who have worked in the IE work, which is the reference design our project builds upon and improves in several metrics. The trade-off is the only trade-off we have over here is lower intrinsic transconductance. But as Sanjay is about to show in detail, the problem has a very clever circuit level solution. Now, Sanjay will explain what happens in the circuit. Sanjay?
Thanks, Upmanyu. Alright, now we get into the actual circuit. I'm going to take you through every transistor, every design decision, every number. So by the end of this, you understand not just what the circuit does, but exactly why it's built the way it is. Uh, okay, let's start at the input transistors as you can see. Let me zoom in a bit. Yeah, so let's start at the input. The input transistors are M1A, M2A, M1B, and M2B. All are PMOS transistors sized at width 20 micrometer and length 1 micrometer. In a conventional OTA, you would connect your differential input V plus and V minus to the gate terminals of these transistors. We do not do that. Instead, V plus is applied to the bulk terminal of M1A transistor and M2A, and V minus is applied to the bulk of M1B and M2B. Why? Because the bulk terminal has no threshold voltage barrier in the signal path. The body modulates channel conductivity through the back gate effect. The relevant parameter here is GMB, the bulk transconductance. There is no minimum voltage offset required. The input can swing all the way from VSS to VDD, true rail to rail, regardless of VTH. That's the fundamental elegance of this technique. Now, the gates of these transistors, they are diode connected, gate tied to drain. This forces each transistor into a well-defined DC operating point. VGS is equal to VDS, so the transistor is always at the boundary of saturation. This creates a stable, predictable, quiescent bias regardless of process corners or temperature variation. The two input pairs form a symmetrical differential structure. When the differential signal is applied at the bulks on one side, on one side's drain current increases and the other decreases. That current imbalance is the signal. Every single transistor in this design has channel length of 1 micrometer. In a 0.18 micrometer process, the minimum channel length is 180 nanometer. So why are we using over 5 times the minimum? Output resistance R0 is equal to VA by ID, where VA is the early voltage. Early voltage scales approximately linearly with channel length. Longer channel means higher VA, which means higher RO. Higher RO means higher voltage gain. In an OTA whose gain is given by GM into R0, maximizing RO is critical when GM is already reduced because we are using the bulk terminal. At subthreshold bias currents in nanoampere range, ID is thin. tiny. R naught can reach hundreds of mega ohms with channel length of 1 micrometer, giving us the gain we need without any additional cascode stages. That would eat into our 0.5 volt headroom. This is not a compromise, this is a deliberate, elegant solution to the gain headroom trade-off. Look at the topology again. A standard differential pair has a tail current source at the common source node. We don't have one. This is intentional and critical. A tail current source requires at least VD-SAT of headroom, roughly 100 to 200 millivolt at subthreshold. At a 0.5 volt supply, that's around 20 to 40% of our entire supply voltage gone just for the tail. We cannot afford that. By removing the tail, we save the headroom entirely. But doesn't removing the tail hurt CMRR? Yes, in a conventional circuit it would. In our design, CMRR is preserved through topological symmetry. The circuit is perfectly symmetric by construction, left and right branches are identical. Common mode signals drive both sides equally and cancel at the output. Differential signals break the symmetry and produce output current. We don't need a tail current source to get a good CMRR, and a simulated CMRR of 97.34 dB proves it. Now let's talk about the biasing. The transistor MB, which is an NMOS transistor, diode connected, sized at width 10 micrometer and length of 1 micrometer. At an external setting, current ISET is equal to 50 nanoampere is forced through MB. This generates a bias voltage VB at the gate of MB. Then this VB is connected to the gates of M3 and M4, also NMOS. Same sizing, M3 and M4 act as current sources in the left and right output branches respectively, mirroring ISET and establishing the quiescent drain current in each branch. Now here's something I'll really like about this biasing scheme. Total power scales linearly with ISET. If you need more bandwidth, increase ISET. You trade power for speed. If you need lower power, reduce ISET. This gives you a single external knob to set the power bandwidth operating point. For ECG, 50 nanoampere gives us 28.67 Hz bandwidth and 17 nanowatt. Perfect for EEG or EMG with different bandwidth needs. You would tune ISET. M5 and M6 are PMOS transistors sized at width 20 micrometer and length 1 micrometer. They form a unity gain current mirror. Here's their function. The input stage produces differential drain currents, call them I1 and I2 from left and right branches. M5 mirrors the current from the left branch to the right branch. M6 then subtracts it from the right branch current. The result is a single-ended output current proportional to the difference. That is, I out is directly proportional to I2 minus I1, which is directly proportional to the V differential out. So this is the fundamental current domain subtraction that converts the differential input into a single-ended output. The unity gain ratio W by L of M5 matching M6 ensures accurate subtraction without scaling errors. Mismatch here would directly degrade CMRR, which is why careful symmetric layout is critical in a real tape-out. This is the heart of circuit that makes the design actually work. Let me be very precise here. The fundamental problem with bulk-driven operation is that GMB will be approximately equal to 10 to 20% of GM. So the transconductance of our input stage is roughly 5 to 10 times lower than a gate-driven equivalent. This directly reduces voltage gain. The solution is partial positive feedback implemented by transistors M7 and M8 sized at W is equal to 14 micrometer and channel length of 1 micrometer. They are cross-coupled. What does cross-coupled mean? M7's gate is connected to the drain of M2B and its drain goes back to M2A and vice versa for M8. The cross coupling here creates a negative conductance at both output nodes. Negative conductance cancels some of the positive conductance at those nodes, which effectively increases the output impedance R out. Since gain is equal to GM effective into R out, Increasing R out directly boosts voltage gain. The PPF gives us approximately 10 dB of gain enhancement. That's the difference between 40 dB and nearly 50 dB of gain. The feedback coefficient is defined as M is equal to GM7 or 8 divided by GM2. We set M is equal to 0.7. Why 0.7 specifically? Because PPF is fundamentally a controlled instability. If M approaches 1, the negative conductance cancels all positive conductance, output impedance goes to infinity, and the circuit oscillates. You want M high enough for significant gain boost, but low enough to maintain stability and tolerable sensitivity to transistor mismatch. At M is equal to 0.7, the gain boost is substantial while the circuit remains well behaved. How is M is equal to 0.7 achieved by sizing? Since both M7 and M8 and M2 share the same L, that is channel length, and the VGS, their transconductances scale with W, that is width. So M is equal to width M7 divided by M2 is equal to 14 micrometer by 20 micrometer, which is exactly 0.7. Exactly, that's not a coincidence. The sizing is directly derived from target feedback coefficient. Now the full effective transconductance expression is GM effective is equal to 2 into GMB1 into 1 plus P by 2 divided by 1 minus M plus P, where P captures the output conductance terms. At M is equal to 0.7, the denominator becomes 0.3 plus P small, which amplifies GM effective significantly. This is how the circuit compensates for the low GMB of the bulk driven input. All simulations were run in Cadence Virtuoso Spectre using GPDK 0.18 micrometer CMOS PDK, which is GPDK available there. Supply VDD that we chose is plus 250 millivolt and VSS is equal to minus 250 millivolt, a split supply totaling 0.5 volt. The split supply is itself a choice. It allows the input common mode to sit naturally at 0 volt right at the midpoint of the supply, maximizing symmetry. Load capacitor CL is equal to 15 picofarad from the output to the ground. This represents a realistic electrode interface capacitance in a biomedical application. For AC analysis, I applied a differential AC stimulus of 1 volt magnitude at V plus and 1 volt at 180 degree at V minus with DC bias at 0 volt. Open loop gain is read as dB20 V out by V in. Frequency sweep from 0.1 Hz to 100 kHz, 100 points per decade, wide enough to capture the flat band gain, the minus 3 dB corner, the unity gain frequency, and the phase margin. For CMRR, I drove both V plus and V minus in phase at 1 Hz, measured the common mode output, extracted ACM, then computed CMRR is equal to AD minus ACM in dB. This is the standard measurement methodology. For slew rate, transient simulation, measuring the derivative of the output response. Let me walk you through the results one by one because each number tells you a story. Open loop gain 49.86 dB, that's about 309 voltage, 309 times the voltage. Flat from 0.1 Hz all the way to approximately 30 Hz, then rolling off at clean minus 20 dB per decade. This PPF is responsible for getting us to a 50 dB with bulk driven inputs. The reference design achieves 54.7 dB using self-cascode composite transistors, more complex devices that further boost the R out. We are 5 dB lower because we used a simple single transistor devices. We are fully aware of this and it's called out in our conclusion as future work. Let me browse to the table so that you can compare our design with the circuit, with the reference circuit. Yes, so this is the results that we got. So unity gain frequency 9.058 kilohertz. This is actually higher than the reference 6.18 kilohertz despite our lower gain. Why? Lower gain means the gain curve crosses 0 dB at a higher frequency. Gain bandwidth is equal to constant. and with lower gain the UGF shifts up. For each ECG this doesn't matter. What matters is gain in the signal band. But a higher UGF gives you more flexibility for closed loop configurations. 3 dB bandwidth, that is approximately 28.67 Hz. The dominant pole is set by Fp is equal to GM effective divided by 2 pi into the load capacitance. At 50 nanoampere bias and 15 picofarad load, this comes out to be 29 Hz, perfectly positioned to cover the ECG band of 0.05 to 150 Hz. This is not a coincidence. The bias current and load capacitor were chosen together to place this pole appropriately. Phase margin 80.36 degree. This is excellent. The minimum for stable closed loop operation is 45 degree. Comfortable is 60 degree. We are at 80 degree. The single stage topology is the reason. With only one dominant pole, the phase doesn't accumulate more than 90 degree total, giving inherently large phase margin. For no compensation network needed, which would otherwise heat headroom or add complexity. CMRR is at 97.34 dB. This is where we actually beat the reference significantly. They achieved 75 dB, we got 97 dB. Let me explain why. ACM is equal to minus 47.34 dB. ACM is common mode gain at 1 Hz, and AD, that is differential gain, is equal to 49.86 dB, and the CMRR is basically the subtraction of the common mode gain and the differential gain, which leads to 97.34 dB. The non-tail topology gives naturally high symmetry, which suppresses the common mode gain, and PPF boosts the differential gain without affecting ACM, because PPF acts on the differential signal path only. Together, these push the CMRR well above the reference. In practice, this means 50 Hz mains interference on your ECG leads is rejected by the factor of 232,000. The ECG signal comes through clean. Power, that is 17.02 nanowatt. The hand calculation is simple. We supply into I set into the two branches. That is 0.5 into 15 into 2. That is approximately 15 nanowatts. We got 17.02 nanowatts. The extra 2 nanowatt is the bias network overhead from the MB transistor, which is an NMOS transistor that we have used. So this is the lower than the reference 31.3 nanowatt, again because we use simpler single transistor devices that have lower the overhead. The price is 5 dB less gain. Slew rate is approximately 2.55 into 10 to the power minus 10 volts per microseconds. This looks shockingly small, but it fundamentally doesn't matter for our application. Slew rate is set by SR is equal to I set divided by the load capacitance, which is 15 nanoampere by the 15 picofarad, which is 1 volts per millisecond. For an ECG signal at 5 millivolt amplitude and 150 Hz maximum frequency, the required slew rate is 2 pi into 150 into 0.005, which is approximately 4.7 millivolt per millisecond. We have more than 200 times that what we need. Slew rate is simply not a binding constraint in nano power biomedical amplifiers. Looking at table 2, which is actually projected here, we match the reference exactly on supply voltage and technology. We are 5 dB lower on the gain, acceptable for simplified single transistor implementation. We are higher on the unity gain frequency, higher on phase margin, dramatically higher on CMRR, that is 97 versus 75 dB, and lower on the power consumption. Overall, this is a very competitive result that we have managed to produce. The path of recovering that 5 dB is straightforward. Replace the single transistor input devices with self-cascode composite devices, essentially two transistors in series configured to act as a single high R-out device. This increases the output resistance further and pushes the gain above 54 dB. That's the primary recommendation for our future work. To summarize what we have built, a 0.5 volt 17 nanowatt bulk driven OTA that achieves 49.86 dB gain, 80.36 degree phase margin and 97.34 dB CMRR, simulated and verified in Cadence Virtuoso Spectre on a 0.18 micrometer CMOS process. Every design choice in this circuit is driven by physics, Bulk driven input for 0 VTH headroom cost. No tail current supply for headroom. Channel length is 1 micrometer for a high R out. Partial positive feedback for M is equal to 0.7 for gain recovery, and 15 nanoampere bias current for nanowatt power with adequate bandwidth. This is a complete simulation verified analog design, and we believe it demonstrates strong suitability as a front-end amplifier for ECG and other lower frequency biomedical acquisition systems. Thank you so much for our presentation here. It ends here.
Thank you.
Thank you.